Good morning, everyone. Welcome. And before we start, I would like to remind everyone that there are new posters. So every day the posters change. So there's a new set of posters hanging in the break areas. It would be great when you have the breaks, go and visit them, talk to the people. We like this part of the event. Now, this morning, I would first like to introduce you Philipp Tomsich. He is the chief technologist and founder of VRULL. It's a software engineering company building software ecosystems, enabling next-generation silicon solutions for ARM v8 and RISC-V architectures. Philipp also sits on the RISC-V International Board of Directors, and he's the chair of the Applications and Tools Horizontal Committee, and he has a master's degree and a PhD from the Technical University of Vienna. Philipp?
Thank you, and I'm really glad that some of you made it after last night's event. So I'm here today to talk about one of the driving factors of RISC-V and one of our key differentiators, really, or I guess the differentiator that we can modify our ISA, add custom instructions is well understood after the last couple of days of presentations. So maybe we focus more onto how this is playing out in the real world and where we have the additional chances to double down on this, to adapt our behavior, to strengthen our behavior in order to have workloads and software really influence what we do with our RISC-V ISA, how to evolve it, and how to get the best for our users out of it. So I frequently open with a quote from Pat Gelsinger recently on all my talks. So he's frequently quoted to say, delivering silicon that is not supported by software is a bug. So this focuses a lot on the enablement challenge. So you're getting software out there, your compiler doesn't fully recognize all your instructions. I mean, it happens in RISC-V too, so we aren't perfect yet. Or other parts of the software stack simply do not get the best out of the silicon you have. That certainly is a shortcoming that you want to address, but that is the enablement challenge. Enablement comes after you have defined it, after you have built it. Well, actually it should come while you do it, but it becomes visible once you have it out. And it is not the focus of what we as RISC-V International are necessarily doing, because we have a much more forward-looking view. So when we specify a new extension, when we specify a new standard, this is not about do we already support it at that point, and how is the support going to look while we consider that as part of our processes. Our question is, what can we specify, what should we specify to get the best out for our users? So in other words, let's modify that statement a bit and look at it from the specification perspective. So if we specify standard, if we specify extensions, and then in extent, if our implementers deliver silicon that fails to optimize for the workloads we have out there in the field, that is a missed opportunity. So you can fix the bug of not enabling it or not sufficiently enabling it by addressing that quite late in the game. But if you do not specify the necessary instructions, if you do not have the necessary hardware support, the hardware will be out there, and you will have missed that opportunity for a whole generation of implementations. So another slide I'm showing quite frequently. On the software side of RISC-V, in our ecosystem, we're really about three pillars. And these three pillars really flow into unlocking performance, unlocking value for the downstream users of RISC-V. So anything we do in RISC-V, it's not standalone. Nobody is done when the silicon is built, when it is delivered. This is about enabling end users to actually gain value. So a lot of panels I attended are really about how do we move product? How do we get RISC-V out there, drive adoption? So why stop at 10 billion cores? Why stop at 50 billion cores? We're here and we're a growing community here because all of us believe that RISC-V is going to be the standard instruction set of the future. And in order to enable that, what we want to do is stop people from fragmenting, from creating new instruction sets, because it suits them better in one or another application, but be a basis for all of them to converge on RISC-V. So for that, very much user-driven, we want them to have, going back from the right to the left, the best software support out there. Because the best software support, the most optimal software support, fastest software, most compact, whatever the specific application domain needs, is what is going to drive the adoption in the market, what is going to drive new designs, what is going to drive value being unlocked by RISC-V. We're doing that as part of RISC-V, and this is just a plug for my horizontal committee for the applications and tools one, by reaching out, by working with the open source projects upstream, by helping out, providing internal vision on what best suits into software, what software requirements are out there, helping on the quantitative data, and just generally providing the glue between the architects and the real-world application. But stepping back from that, so this is great. I'm arguing that we want as many custom instructions as possible for every single market. I know the next thing everybody's going to worry about is, so how are we going to run software and port it back and forth? So yes, the F word is frequently coming up, fragmentation. This is a big concern in what we're trying to address, how we're trying to manage it. I could hold entire technical talks on the various mechanisms that we have, starting from the discovery over to how do we have a single binary distribution out there, and profiles, platforms, all the standardization efforts that are going on. But we don't just want to manage fragmentation, we also want to enable differentiation. So again, the user wants the best performance. In order to get the best performance, they will want custom extensions, they will want custom instructions, they will want a mix out of all these extensions that we're defining, and that means they want to differentiate their product. Things that we need to do on the software stack, that we need to do in the software ecosystem to ensure that this works, that you can have extra extensions on top of a basis, but still have an interoperable basis. And all of that goes back to what I said before. We want to foster adoption. We want to foster the uptake. We need to make sure that RISC-V is usable as it is out there. Now, RISC-V is quite interesting. I always refer to the slide as the unique selling point of RISC-V. We are both modular and extensible. And we're the only instruction set out there that gives users this freedom this easily. So they can actually leave off instructions, features that they don't need. I mean, if you look at our specifications, this is really a construction kit. You can add, you can remove. So if you're going down in terms of the performance requirements, in terms of the size you want, if you're getting more specialized, if you don't want to run standard software, you have the modularity of leaving things off. You can still use the standard tools, same tool chains, same libraries, and adapt them to your use case. On the other hand, we scale up. So you take the center of gravity and you add things onto it. Custom extensions, you customize our vector instruction set for longer vectors. So there is a lot of flexibility there. And the goal on this side is to really roll out innovation while reusing the basic infrastructure that we have. So make it easy for users to congregate onto RISC-V, to converge on it, while giving them the ability to address their specific target markets easily. So how do we do that? So what are the approaches? And I'll have to get a bit technical and process-oriented here for a few slides, because we have seen that there is multiple players approaching that, coming from different sides. So we have the goal of having something that works between as many users and as many implementations, but everybody wants to add their own performance optimizations, their own extensions. And RISC-V, as far as the software horizontal committees are concerned, is really about 3 layers of improvements that we can provide and that have different trade-offs. So we can go in and just optimize the code generation, add information about the core. It's still the same code. It's going to run everywhere. This is what everybody else does. So you just recognize what your microarchitecture does. You put it in the compiler, it's going to select the right instructions, perform the instruction scheduling, and so on. This just adds a bit of a complexity burden and maintenance burden on the software toolchains, but otherwise doesn't have much of a consequence. It gives you a base level of performance. Everybody is doing it. RISC-V is not really differentiating itself that much by it. But then if we go up, we can use the same architecture, new instructions, just workload intelligence, inspect what is running, how is it running. An example of a microarchitectural optimization a lot of people are doing and talking in the RISC-V ecosystem on the high end is microarchitectural fusion. So you take a couple of instructions, the pattern is suitable to be implemented in a customized micro-op, you just do that. Again, a bit of increased complexity for tool chains. We need to know the chips are doing that. But there's, in reality, diminishing gains for software. So there's a couple of common use cases that you will fuse, you will get there, and then more effort, fewer gains at some point. And finally, and this is where we can really use the hammer and squash the problem of individual workloads, we have the architectural improvements. Specialized instructions, ISA extensions, things that differentiate us for individual markets where we have conditional operations for the high-end market, where we will have SIMD and integer registers with DSP-like instructions at some point. So a number of specification efforts that are really targeting to give a lot of an improvement with just getting the instructions right and getting the definition of those right, with one drawback. This is going to consume opcode space. And we're exhausting our 32-bit opcode space. We have exhausted our 16-bit opcode space with the compressed ones. We're moving to 48 to 64 bits. Again, a burden. So what is the underlying question to stop this crazy growth? Opcode space running out, everybody having a slightly increased maintenance burden. Well, the only way we can do this and really make sure that we do the right thing is to have a trade-off. What is my workload? What are the quantitative observations that we have? And then we define that. In the past, a lot of the new ideas, new proposals were coming out of what did other architectures do? What is theoretically possible. And over the last 2 years, we've been very good in injecting more and more quantitative data and actually doing the entire cycle before we specify something. So we need to root all of our new instructions and instruction definitions in fact-based decision. And this is what's happening today. This is really what RISC-V and RISC-V International is about. And if you're in this room, this means you are, in one role or another, participating into exactly this process. You're feeding into this process, you're on the decisions that we make, and also on the judgment calls that are part of this. So we have the evolutionary drivers for our ISA. It can be benchmarks, it can be real applications. If you're doing motor control, it's going to be very different from a DSP application that sits in a hearing aid, or if you're building a supercomputer. And all of that means you have specific workloads. They will have commonalities, but you have specific workloads. We're interested in those. We're interested into the inside of those, in the specific needs of each of those, and that will flow into experimental tool chains, emulation of the instructions. All those are working groups within RISC-V. All of those are data sources, because you have your application, you build an emulator that has a proposal implemented. You have a tool chain that targets this, and you will feed new information back. That new information then feeds back to the proposal. So it is a a bit of an iterative process. And this is really how our last couple of instruction extensions over the last year have evolved. So first of all, there have been fewer big bang instructions. So vectors has taken, and I guess many of you know better than I, 6+ years just to get standardized. But over the last year and a half, we had a couple of them that were flowing really quickly. We had fast tracks, we had smaller extension packages that were going through. One example is CFA, the floating point gap fillers. Doesn't really sound like a very glorious instruction package, I mean gap fillers. But then again, it is actually derived from, some of these instructions, and they're actually derived from quantitative analysis. SpecFP, other workloads, and they are really designed to reduce dynamic instruction count. They came out of looking at the benchmark, looking at the instruction stream, looking at the traces, and determining that rounding of floating point numbers was actually quite a common occurrence. But we didn't have a rounding instruction. We were converting them to integers, we were converting them back. So what happened is a rounding instruction got introduced. That one was actually measured against real benchmarks, and we had performance numbers. So not just that we knew this has a real-world benefit and how much, we also knew what we're getting back for the opcode space that we're consuming. Similarly, we have the loading of floating point constants directly as a floating point immediate. And the design of that instruction, again, quantitative analysis, what kind of immediates are we seeing? And there's, even now late in the specification process or in the standardization process, still discussions about the quantitative observations from embedded versus larger software bases. And all of that also fed into how many bits do we use in order to represent these floating point immediates. I think ARM has about 8 of them to represent and decode. We had just 5 bits available, or we were just dedicating 5. And again, this is a trade-off. You see the quantitative data, you say how much do I want to cover, and how much of my opcode space do I want to give up? Because we're, in a way, quite mature. We have all the basic things standardized. We have a full vector instruction set. And at this point, we need to look at how much opcode space are we giving up, because our 32-bit opcode space is limited. There are only so many new instructions that we can add, and only so many new opcode points. So the code points are really the problem. An instruction is easy. That's one line in a specification. But if you need the space to have all of your immediates, if you have a 12-bit immediate field in there, that is a lot of code points that you're taking out of your 32-bit space. Another example of how this process has been progressing over the last year and how we've been making great progress in feeding back quantitative data has been conditional operations. Again, driven by actual benchmarks, looking at the RISC-V philosophy on how it can be done, and then re-evaluating against real-world benchmarks. And that is a case where we're getting a small benefit on average, unless somebody does quite glorious fusion on the back end, and where that has informed the choice of how many opcode space points do we give up on it. So 1% gain, just a few points given up, a very good return on the investment of opcode space. Now, the most important thing to this is our extensions originating from software applications, as we have seen over the last year and a half, tend to be small, tend to be focused, and tend to be lightweight. So if you're doing the bottom-up experiment, if you're looking at what does the software do, and then you design a targeted solution, you're getting less instructions out of it, you're getting a faster process through the extension. If you're doing the heroic effort, something like vectors, where you know this is something I have to do, I have to cover my design choices, I have to look at the entire possibilities, you will be slower. You will get both a larger extension and you will be slower in getting to the goal line. Being faster allows us to deliver the benefits of RISC-V incrementally. So we see something in an application, we see something in an area that the implementers want to move into, we identify the opportunity, we specify it, we move forward, and we manage the fragmentation aspect. Because even if not everybody is going to implement an optional extension, it is better if we have only one optional extension to target that than if everybody does a vendor-specific one. So, to close the circle to what I said in the beginning, I'm running the Applications and Tools Horizontal Committee. We have plenty of groups. I'll briefly introduce those that are on this slide, because not everybody is closely involved and may know what they're doing, why they're doing it. We have a number of groups on the Applications and Tools side. We have a number of participants in there that are looking at specific application areas. We're very open to adding more groups, looking at more application areas, because as I said, this is driving our evolution, this is driving our direction. And right now, the key ones that are driving specification efforts at the moment are managed runtimes. They are looking at anything that is a managed runtime, whether it's Java, Python. So basically, you have your special purpose language, you have a runtime, you have your entire stack that you want to optimize for. And this is the one group trying to port this into RISC-V, or actually coordinate the porting in the upstream projects, and bring back requirements that they see where we either have gaps versus other architectures, or whether something that we could do in the future will be beneficial. And they have 2 fast tracks in flight at the very beginning, because it hasn't been put out to the architecture review process and all of our internal processes of trade-offs, but it is being circulated, it is being discussed in the respective group at this point. One of them is a dynamic per process switching of CTSO, so autocorrection hit me there, strong memory to weak memory model switching. That one is requested by a number of people that want to do emulation, that want to switch to a TSO mode eventually, but not have the penalty for every process in the system. And the second one is a user mode memory management fast track that's going to benefit garbage collection in our Java runtime. So certain garbage collection algorithms benefit from, well, additional instructions and additional state. AI and ML is another group that has been very active. They actually been working on that proposal together with graphics. So AI ML is a group that is looking at multiple things for RISC-V. What do current AI workloads need? What do they do? How well do we fit with what they require at this point? And where is the anti-AI ML space heading relative to where we stand? So step 1, fill out all the gaps, make the software that's out there perform well. Step 2, identify where can we become a leader as RISC-V by preempting, by envisioning the next trends and being there when they happen. At the moment, their biggest concern is matrix operations. This is not going to be a fast track. This is quite a big thing. Will be specified or will be put up to the vector SIG, which is on an entirely different part of the standards body and has governance over anything that's MD. But the requirements are being driven out of that group. What benchmarks do we run? What operations do we see? How big are the matrix blocks that we want to operate on? The Android SIG has, well, you've heard it yesterday as well. The Android SIG has been working hard over the last couple of years with a number of industry partners to help drive Android readiness on RISC-V. There's a number of companies contributing to it. They are working through the SIG to meet up to see what is needed, and they have been proposing the memory coloring, which is, I shouldn't say the word, but similar to ARM-MT in Spirit. So you have a memory tag. In their case, they call it coloring, they call it palette memory. It's a way to attach additional information to an address and to an address range, and then simply see who has access to it, can we access it at any given moment. Primarily a debugging tool. And finally, RVM CSI. On Monday, there was a talk from that group. This is focused on the small microcontroller area. Again, not going to be a fast track. This is a big thing. This is a specification. There's a task group coming up. This is more like a 1.5 year, 2-year effort. And this is actually non-ISA. So no new instructions, just a specification effort coming out to make RISC-V existing specifications and the way our ecosystem builds up solutions more digestible to software. So a call to action, something why we need to talk about this. This is really, if you see something, say something. We have a lot of different stakeholders in our system, in our ecosystem. We have architects contributing, we have micro-architects, software engineers. Software is a wide area. You have systems, you have various applications. If you talk to somebody who is doing HPC, they will know more about floating point. If you talk to one of the people implementing Java, you will have more of a focus on dynamic execution, fast just-in-time translation, and similar topics. So depending on who you talk to, they have specialized knowledge. Again, architects, micro-architects, software developers, and all of them need to come together in order to make this an efficient process. So it's not just if you see something, say something, but we need to get together. Look at your workloads, observe them. If we don't cover your specific application areas, come to us, tell us we need to set up a SIG with some like-minded people to bring the discussion inside of RISC-V on what specific application areas out there are doing. Even if there are new application areas emerging we might not know about. And help us drive the evolution of the RISC-V instruction set architecture in order to make it even more on point, even more performing and optimized in the future. We can't do it alone, we can't do it top-down. This is really a process that needs to be collaborative and requires all the disciplines involved in this. Architects, micro-architects, software, to come together and help us move this forward in a targeted way. And the benefit we're getting out of this is we're faster, we're more agile, we have more fast tracks, we have more smaller extension sets, and we can roll out benefits iteratively instead of doing this big bang and just defining it top-down. So, thank you for your attention. I don't know, am I taking questions?
Sure.
So, to be honest, the heroic effort goes to the entire audience for coming here at 9 a.m. after the social event. So, any questions?
There's always a danger that at the same time the processor itself gets slower in megahertz. Let's say it gets 20% slower, then you haven't actually gained something, you have lost something. How do you make sure this doesn't happen?
So that's the point where I said we need the micro-architects at the table. Because a small change in how we define things can make a large change in how applicable this is or how easy it is to implement. So first of all, most extensions that we define are optional. Most of them. But they tend to slowly seep into the standard because people find them good, software targets them. So if we define it, it eventually will need to be implemented by multiple people. And the only way to do that is to get the micro-architects on early. They usually come on quite late, but it's too late once the specification is out in final review. We want them on early, and as I said, we need all 3 levels. The architects are great, but the micro-architects need to be in there. And some of the discussions that you may have seen on the ISADEF list over this year are more geared against that people are saying, well, I don't really think this is a good idea, or it should have been done differently because it's going to impact my microarchitecture. But once we're in public review, it is usually a bit late. So we need to get that feedback cycle early and see that we get the definition just right for a large consensus of the ecosystem.
Thank you.
Thanks a lot, Philipp.